Hello everyone, I'm Christian Duran. I'm going to introduce you to an instruction set verification or RISC-V based processors using the best of functional simulation and formal verification IP. This work is made with collaboration of the Universidad UCL de Santander, UIS, and the Politécnico de Torino. For the outline of this presentation, first we talk about the motivation of this work. After that, we will talk about the functional simulation for ISA verification using genetic algorithms. Next to that, we will introduce a similar approach for ISA verification using formal. Lastly, we will discuss our findings. We will now hop to the motivation of this work. The figure in this slide depicts a processor of 3 stages will be tested for the ISA verification. The components included in this architecture should comply with the RISC-V ISA to support the integer and the multiply extensions. This architecture will execute programs loaded mainly into the instruction memory. For the software perspective, several kinds of programs should run on any processor and produce the same result. Testing for each software scheme is a difficult task which involves tortuous programs. This is where the ISA verification is involved. Let's talk about performing functional simulation for verification. In the simulation environment, we have two scenarios where the program execution is compared. The first one is the processor itself, and the second an ideal execution model. This comparison is performed several times with different RISC-V programs. Each time both the processor and the ideal model execute one instruction, components of the execution are compared one by one, highlighted in red. The final objective of the simulation is to cover most of the cases of each instruction type. The coverage metric is given by a coverage extraction tool. We maximize the cover percentage of the processor using genetic algorithms which produce the torture programs. The genetic algorithm, named MicroGP, has constraints containing the program structure for RISC-V ISA extensions. Additionally, it contains characteristics of the population and the execution environment to perform. MicroGP will read these constraints and generate the first population of RISC-V programs. When executed, the coverage will be extracted and maximized by MicroGP during the algorithm. The test by itself is running all these programs in both the processor and the verification, or POV, and the RISC-V ISA simulation spike. The execution per each instruction is extracted and compared. Any difference between the execution in the two environments will be stored in the stack to be debugged afterwards. The next verification procedure is RISC-V formal. In formal verification, we have a deck of formal checks, each one defined for each instruction defined in the ISA specification, plus some others to verify continuous execution and data consistency. For example, the instruction add have two rules to check against. The first being to constrain the executed instruction to be an add in the matching code, and the other to check the sum of the source operators with the result. The formal verification architecture is as follows. The formal IP needs an interface named the RISC-V Formal Interface, or RVFI. To create the interface, the final status of the execution needs to be output. We create additional segmentation components of the execution status on each of the pipeline stage. When the POV returns an instruction, the components are published to the interface. From here, each one of the formal properties defined in the RISC-V Formal IP are tested against the POV results carried by this interface. Each one of the formal IPs are specified according to the ISA specification given in the constraints and clauses forms. Now we will present our findings using the combination of these approaches. We found a discrepancy when trying to test the interrupt triggering. During a certain instruction, the test auto-triggered the input, causing the program counter to switch to the exception vector empty vec. The difference between the processor and spike resides whenever the instruction should set the MAPC before or after the execution of the interrupted sequence. In the case of the POV, the instruction in PC plus 4 virtually got executed 2 times, before and after the interruption handler. This does not occur in a spike due to the nature of the interventions. This leaves us with an absence in the specification regarding the interrupts. Two possible scenarios are capable of fixing this problem. The first one is to insert bubbles in the interrupt sequence, totally blocking the execution on the interrupted instruction. Another one is to left flush the pipeline stage before interrupting. This makes the interrupt take some delay, but maintains the execution status regardless of the pipeline stages. The previous discrepancy was detected by the microGP and SPI functional verification. Another test performed in this verification tool was to insert errors on purpose on different parts of the processor and check around them. Thank you very much.